So we'll finish this off with question 25, which is probably going to be the longest calculation we do. So what is the pH of the resulting solution if 25 milliliters of 0.1 molar acetic acid is added to 10 milliliters of 0.1 molar sodium hydroxide? And then it tells us that the Ka for that acetic acid is 1.8 times 10 to the minus fifth. Okay, so here is what the pH curve will look like for a weak acid. So HA, the weak acid HA plus OH minus, what's that going to make? It's going to make H2O, and it's going to leave behind the A minus. Now, at the equivalence point, we've already talked about that. That is where we've added exactly the same number of moles of OH minus as we have HA. That'll occur right here at whatever volume we have to add. And that pH, we already showed, because of the presence only of that A minus, that pH is going to be greater than 7. It's going to be basic. And then we have another region right here. This region right here, we'll have done part of the titration, so we've added less or fewer moles of OH minus than we had HA. And so there's going to be a mixture of HA in there and of A minus. So in this region, this is where we use that Henderson-Hasselbalch equation, and that's going to be the pH is defined at that point to be equal to the pKa plus the log of the ratio of the base concentration over the acid concentration at that point. That's what's going on right in this region right here. Now, right here, when we haven't added any base at all, that's just the equilibrium from HA plus water. We already did a problem like that. And then up here, it's going to be, I've added now more base than I have HA, so it's going to be dominated just by me pouring OH minus into that liquid, and that will give the concentration. So right now, what do we have? Where are we? Well, we're at, so for the HA, our starting amount here is equal to 0.025 liters times our 0.100 mole HA per liter. And then we have our OH minus that we're adding, and at this point we said we've added 10 milliliters, so 0.010 liters times, in this case it is 0.100 moles of OH minus for every liter. And so those values tell us how many moles of HA and OH minus we've added. So when I simply do those multiplications, these are the values I come out with. So this is how much HA we start with, and this is how many moles of OH minus we've added. So because we've got that HA reacting with the OH minus, that makes water, and it leaves behind A minus. That also tells us how many moles of A minus. However many moles of OH minus we've added, we're going to have that many moles of A minus. So we're going to take, to find out how much HA remains, we're going to take 0.0025 moles, and we're going to subtract from that 0.0010, and that leaves us with 0.00015 moles of HA remaining. Because this reaction occurs, OH minus plus H2O to make water, and leaves behind the A minus, this amount right here, the amount of A minus I have is equal to the amount of moles of OH I've added. So that's equal to 0.001 moles of A minus that are there. And then we have to use our equation, and I'll do that now. So we'll use Henderson-Hasselbalch, so it's going to be the pH is equal to the pKa plus the log of that A minus concentration over HA concentration. But because these are concentrations, it's per liter, per liter. Those are going to cancel. We can just put the moles in there. So there's our amount of A minus. There's our amount of HA. And our pKa, well, that's up here. So we have to take the pKa of that. So let me calculate that. Now I realize this is difficult to see, but I've just finished this calculation out here, right there. So this is the pKa. It's just taken minus the log of that Ka, okay? And that's 4.74. And then that's the A minus concentration. That's the HA concentration. And so what this turns out to be is equal to 4.56 is the pH after I've added 10 milliliters of the 0.1 molar sodium hydroxide. I know that's messy. I'm sorry. I hope you can follow that to get to the right answer. And that is graded homework 3 problem set.